So what is an ice table? An ice table helps you track how concentrations change in a reaction as it moves towards equilibrium. We're going to use the exact same I is your initial concentration, C is the change, and E is your equilibrium concentration. I usually also include R, which would be the reaction. So either ice or rice tables. How we're going to use an ice table is that we have to start with a balanced equation always. And then we'll set up the table. We're going to list each substance, the reactants, and the products. We're going to fill in the initial values, which are generally told to you. We're going to use the given concentrations, and if none are given, assume 0, especially for the products. Like, meaning we're just starting with reactants, they haven't started reacting yet, so we don't have any product. Then we're going to determine C, which is the change. We're going to use the variable, usually X, like just a very common variable. For our reactants, we're going to subtract X, and for products, we're going to add X. Now, this addition subtraction can change when we compare Q and K, and I'll kind of explain that a little, but generally we're subtracting our reactants and adding our products. Then we'll multiply by the coefficients if needed. Next, we'll write the equilibrium expressions, that's E. And we're just kind of adding down the column. We'll take the initial concentration and add the change for our products or subtract the change for our reactants. We'll plug that into the equilibrium expression, which is K, what we did in the last lesson. We'll solve for X and then find our final concentration. I like to use the rice table, so I'm going to rewrite my reaction. I have hydrogen and iodine in equilibrium with 2 hydrogen iodides. My initial concentrations are generally given. For iodine, our initial concentration is at 1 molar. Or I'm sorry, for hydrogen. For iodine, the initial concentration is also 1 molar. And for the hydrogen iodide, there's nothing at the start. A lot of times for your products, there isn't any concentration at the beginning of the reaction. We are going to use this K equals 4 in a moment. For my change, it's going to be based upon the coefficient. So because there's no coefficient, I'll just say minus X. Same for I2, minus X. But because there is a coefficient here and it's a product, I'm going to add 2X. So subtract for your reactants and add for your products. Once I get to the equilibrium, I'm just going to add those two previous, the initial and the change. So 1 minus X, 1 minus X, and then 0 plus 2X or just 2X. I'm going to go ahead and write the equilibrium expression like we did in the last lesson, where K equals the concentration of the products to the power of the coefficient over the reactants. Neither reactant has a coefficient, so no exponents. Then I'm going to plug in these equilibrium values from my rice table. HI is 2X, and that whole value will get squared. On the bottom, H2 is 1 minus X, and so is I2. I'm going to simplify what I can. 2X to the power of 2 would be 4X squared. On the bottom, 1 minus X times 1 minus X, I can rewrite that 1 minus X squared. I also know K. K is told to us that it's equal to 4. So I'm going to set that expression equal to 4. And my goal is to solve for the X. So the first thing I'm going to do is take the square root of both sides in order to get rid of those squares. So that's going to equal 2 And then on the other side, I'll have 2x over 1 minus x. So it gets rid of those exponents of the 2 by taking the square root. Next, I'll multiply both sides times that 1 minus x. So I'll have 2 minus 2x, and then just left with the numerator on the right. Then I'm going to try to solve for x by dividing both sides by 2. I can take the 2 out of this expression here. And then I'm left with 1 minus x equals x. 1 equals 2x. And finally, x equals 1/2. Not quite my final answer. That's what x is equal to. So I'm going to bring that back up to my Rice table and solve for the concentrations at equilibrium. So 1 minus the 0.5, 1 minus the 0.5, and 2 times the 0.5. So my equilibrium concentrations, I'll be able to find them now. So the equilibrium concentration of hydrogen is 0.5 molar. Same for the I2. And then the concentration of HI is going to be 2 times the 0.5 or 0.25 molar. This concentration here should be 1 molar, not 0.25 molar. Okay, for the next reaction, we're going to go ahead and fill out our Rice table. Make sure that you have the reaction, and I also modified K a little bit, and I'll explain why in a moment. I think I was also missing the concentration of N here. So my reaction is N2 and 3H2 in equilibrium with 2 ammonias, or NH3. For my initial concentrations, again, I was missing that when I typed it, is 1 molar. Our initial concentration of hydrogen is 3 molar, and the ammonia started at 0. When I think about the change, I'm really only going to be using a variable, plus or minus, and my coefficient. So what's the change for nitrogen? Minus x. What's the change for hydrogen? Minus 3x. And what's the change for ammonia? Plus 2x. I'm going to add my initial and my change. So I have 1 minus x, 3 minus 3x, and then just 2x. I'll start by writing my equilibrium expression, which is my NH3 to the second power because of the coefficient. Then I have N2, no exponent, and then H2 to the third power. I'll go ahead and plug in those values from the Rice table. So I have 2x to the second power over 1 minus x times 3 minus 3x. And that needs to be cubed. I'm going to simplify this as much as possible. 2 squared is 4, and then we'll have x squared. On the bottom, I'm going to kind of factor out a few things before I simplify. From this 3 minus 3x, what can I factor out? A 3. So I'll have a 3 cubed because it was cubed, and inside I'm just left with 1 minus x, and that's still going to be cubed. I did that so that when I rewrite that, I can do 3 cubed, which is 27. I have 1x times 1x cubed. What does that come out to? To the fourth power. Now I'm going to set this equal to the k. I did modify k. 1 times 10 to the negative fourth. The reason that I modified k is so that we don't have to do the quadratic equation and like extensive math. When k is a very small value, very small, I would say like thousandths and less, we can say that 1 minus x is about 1. Like, meaning that x is so small, there's not going to be much change there. So if k is a very small value, like it definitely is here, if I see 1 minus x, I'm just going to plug in a 1 there and assume not much change has happened. It's going to make our math a lot easier. So if I continue with this, I have 4x squared over 27 equals 1 times 10 to the negative 4th. I'll multiply both sides by the 27. Which is a pretty small value. Then I'll divide both sides by 4, an even smaller value. And then how would we get our final answer? Take the square root of that answer. So x is very, very small. It's 0.026. As far as rounding purposes, let's just say 3 decimal places for our x values. Now, that's not our final answer. We're going to use that x value back in our table. I'm going to do 1 minus the 0.026. I'll plug in that x here. And then 2 times the 0.026. I'll go ahead and solve for my equilibrium values, 1 minus 0.026. These are going to not be much change. Because the k is so small, that means that there wasn't much change at all. So 0.974 for nitrogen's equilibrium. 2.922 for hydrogen. And 0.052 for the ammonia. Okay, again, that k changed, so make sure you change it to not just 5, but 5 times 10 to the negative 4. I'm going to fill in my rice table starting with the reaction. So I have CO, which is carbon monoxide. I have 2 hydrogens, and then I have CH3OH. Then I'm going to fill in my initial concentrations. I started with 1 molar, 2 molar, and 0 for my products. As far as the change, we're going to subtract our reactants. I'm going to subtract 2x because of that coefficient, and then I'm going to add my products. When I figure out my equilibrium, I'm just adding those 2 columns together. So I have 1 minus x, 2 minus 2x, and then x. I'll start by writing my k expression, which is my products over the reactants. No coefficient for the product, no coefficient for carbon monoxide, and I'll raise hydrogen to the second power. I'm going to plug in the values from the ICE table. So for the product, I have x, then over 1 minus x times 2 minus 2x squared. Similarly to the last question, I'm able to simplify the bottom here by factoring out a 2, so that I'm left with 1 minus x. Don't forget to square that 2 that we took out, and that 1 minus x is squared as well. When I simplify, I'll have x over 1 minus x to the third power, because there's 3 of those, and then I'll have 4 on the outside of the parentheses. As I mentioned with the last one, if k is very small, this just becomes 1. So we have x over 4, and we'll set that equal to the k value. X over 4 equals 5 times 10 to the negative 4, and then I'll multiply both sides by 4. So 5 times 10 to the negative 4 times 4 is going to equal 0.002. Then I'll put that back into my expressions wherever I see X. So the concentration for the product is just 0.002. For the carbon monoxide, it's going to be 0.998. And for the hydrogen, it's 1.996. These are all concentrations, so they really should have an M with them.